All right, so we have been talking for the last couple of days now about this idea of a function as a way of sort of relating two things together, right? So again, kind of our default thing is we've got one set of values that we call the domain that we think of as like input, and kind of our, again, like default thing is going to be, that's the thing that we label as X. The function does its thing. It pairs those off with output values or Y values that belong to a set called the range, right? So domain, range, the function's the thing that maps in between them. And if it's really a function, then what it does is take one thing from here and send it to just one thing here, right? So for example, this one that we looked at yesterday, f of x was 2x plus 3. So that takes a thing, multiplies it by 2, and then adds 3 to the result, right? And again, we use f of x or y kind of interchangeably, right? As being like the output thing. So we found, like, for example, f of 7 means, okay, let x be 7. If I rewrite that with 7 in place of x, I get something that looks like this: 2 times 7 plus 3. I do the arithmetic, I get 17. So 7, 17 are paired together, right? The x and the y from the elements from the domain and the range. 7 maps to 17 for that specific function, and a different input value would, go somewhere else, right? But again, the important part is that for 7, but also for other stuff, every time I plug 7 into this, I'm going to get, the same result back. I'm not going to get something else the next time I try to do it, right? That's what makes it a function. Okay, and the thing I left off with on Tuesday was asking you to think about the domain and range here. So another way that we could look at this function that we haven't done just yet, or we haven't done as a group anyway, is to look at its graph. So there's the graph, y equals 2x plus 3. You've seen this kind of thing before. It's a linear function, so it's got y-intercept at 3 and slope 2. So, think back to whenever you did this before. You might, start by, like, if you're going to graph it by hand, right? You plot the point at 3 on the y-axis, and then you do the stair-steppy thing for the slope, right? Go up 2 and over 1, right? You draw another point, then you throw a ruler on there and draw the whole line in, right? Okay, the reason you draw the line in is that it's not just those like nice points that have nice coordinates that you land on when you do the stair-steppy slope thing, right? But it's everything in between as well. So this goes through, 0, 3, and it goes through that other point we found, 7, 17. But it also goes through a whole bunch of other stuff in between where the coordinates, may or may not be quite as like nice, right? Might not look as pretty. All the decimals and fractions and stuff we don't even know how to write down, those are there too. That's why we draw a solid line like that. Okay, so with all that in mind, and with this thing, looking like it does, we'll get a little bigger picture of it so we can see more. What do we mean, or how can I see here what we mean when we talk about the domain and range for that function? I don't think I have it. Domain is the set of all the x values. Just as a reminder what the terminology means: range, set of all the y values. Okay, so what we do with the last example we looked at last time, right? We had a list of people and a list of their heights, right? If you want the domain and range, you just write them down, right? Because you can make a list of 20 things. Can I list these out? I can't list them, right? Because it's not just the, it's not just 0, 1, and 2, and 3, but it's all the messy stuff in between those too, right? I mean, even if it was just those, there's still too many of them to write down, but also it's the stuff in between. So I can't just list them, right? What can we describe them? Domain's all the x values. So if I look at this and I think x values, well, the x-axis is this horizontal one. So is there anything that's left out? Can I go to -20, for example? If x is -20, can I find the function somewhere? Yeah, there it is, right? Okay. And if it's, I don't know, 40. Well, okay, there it is. It's up there off the screen, but it's up there, right? So is there any time that I wouldn't be able to do that? Does it cut out or stop anywhere? Or does it just keep on going? Yeah, it just keeps going, right? Here it is, way out at like, we're out in the like tens of thousands, right? Still looks pretty much the same. Just keeps on doing what it's doing. Okay, so I might describe the domain, the X values, by saying something like it's everything, right? It's defined everywhere. All real numbers would be another way to say that. When we talk about graphing things, we're only interested in real numbers. So don't worry about what non-real numbers are yet. We'll get there later. So I might describe it that way. Okay, what about the range? Now we're talking Y values. Yeah, I mean, kind of same thing, right? I mean, if you're drawing it by hand, you'd put little arrows at the end of the line, right? To show that it keeps on doing what it's doing. Okay, so the domain and range of this, I might say something like it's all real numbers. There's a special symbol for that you might see. I'm not really going to use it, but you might see it in books or online or whatever. It's a capital R, but the vertical part's like double struck. You know, there's like an extra line there. That just means the same thing. That's the real numbers. Like I said, I'm not really going to use that. You may or may not actually see it. Range, same thing. All the real numbers. Okay, let's look at another one real quick, just to kind of maybe hit this idea a little bit more. Here's another graph of a different thing. Don't worry about what it is. That's its graph. This red curve that sort of starts out there and then goes off up and to the right. If I'm thinking about its domain, again, it might help to think about anywhere that I don't see it or that it doesn't exist. What do you see? Yeah, it starts somewhere, right? If I'm thinking about reading this thing left to right, it doesn't exist over here at all, right? So the first time I see this graph show up is at 0, and then from there off to the right. Right, again, sort of going off the edge, we assume that it sort of keeps doing what it's doing. So everything 0 or bigger. Okay, what about the range? Same idea, but we want to talk about the Y values, right? But again, there's sort of a place where it starts, right? It doesn't exist down here at all. It does up there. So what we run into is, that this cord has a short in it or something. There we go. Okay, so we run into like needing to be able to write things down, right? Some way to describe what's going on, because again, there's too many things to just list, right? I can't just write them down because there's too many. So here's a number line, and if you think about or remember the way a number line works, we draw a solid line because there's a bunch of stuff there, and we put little tick marks on it to indicate just kind of where we are, so we have like a reference point, right? I know it's kind of hard to see on your copy what's going on here, but there's a filled in circle here. There's some stuff here that's shaded in red or gray, I guess, on the copies, and an open point there at 3. Okay, so don't worry about the math stuff yet, like how we're going to use proper notation to write it down. If you were just going to describe that, what would you say? Starts at -1 and ends at 3. Okay, yeah, that works, right? I mean, if I say it starts at -1 and ends at 3, you know what I'm talking about, right? Now, there's kind of buried under there, there's this, assumption that I got to know that we're reading it left to right. Okay, assume that we know that we're going to read it left to right. Then I say it starts at -1, it ends at 3. I maybe need to describe, I'm going to, reproduce the picture exactly. I maybe need to describe what happens at the ends, right? So what happens at -1 and at 3 that's different? One of them's included and the other one's not. Yeah, so what these, the shading indicates like you include this stuff. This filled in point here at -1 means the same thing, that's included. You get to -1 and it's like a hard stop, right? You stop right there. At 3, this open point means that it's open there. That means that, if this is 3, you can get as close to 3 from this side as you want, but not actually to 3. So 2.999 all day, that's in the set. 3 is not, though. Okay, so that's what that open point means there. Okay, so we can describe it as, start at -1, stop at 3. I could also describe it as everything between -1 and 3, right? It's, betweenness is a good way to describe this because it starts and stops somewhere. So I could say, okay, what's everything in between those two? So 2 ways that we can write that down. One's called set builder notation and looks like this. I know that, this one looks a little bit intimidating, but the curly braces still just mean this stuff goes together. And then the way that you read this is that it's the set of X values. Okay, so here's a set, the things in it are called X. This little vertical line, or sometimes you might see it with a colon instead, that just means there's some like condition, right? So it's the set of X values that do this thing, right? The set of X values so that -1, well, actually, somebody tell me what this says. -1 is. So we got inequalities, right? So we got to remember what the inequality symbol means.
Well, I can't remember if that's less than.
Yeah, exactly right. 5's bigger than 3, right? So what does the thing do? Right. Right? Because it's a shark or a crocodile or whatever. I like to draw mine as a shark. You can do a crocodile. Yeah, it's a shark. Yeah. So it eats the bigger thing, right? It's not like a whole shark. There. Okay, it eats the bigger thing, right? No, you're good. You're good. I'm not. Yeah. No, I am willing to bet whatever's in my wallet that you are not the only person in the room who wasn't sure which way the thing goes. So, yeah. No, you're good. Okay. So yeah, so the line underneath is or equal to, right? Okay. So this says X is bigger or smaller? Bigger than -1, and also X is smaller than 3. Okay, so this is just between, right? The way you would interpret this is that it's between those two things. This one's okay, this one's included, that one's not, right? That's the line underneath. But okay, so that says the set of X such that X is between -1 and 3, and -1's included and 3 is not.
Wait, what does it mean if there's a line under it?
Or equal to.
Equal to, okay, so what's the other one?
So strictly less than. So -1 is less than or equal to. So X can be -1, but X has to be strictly smaller than 3. So 2.999, whatever, that's okay. 3 is not. Yeah, that's the difference. Okay, so that's there. That's useful for some stuff. It's a little bit clunky and it looks intimidating if, I don't know, it's your 3rd day of college or something, right? And this is the first time you've ever seen it. So another way that we can write that, and the way that we'll do things more often, is what we call interval notation. Interval notation does exactly what JK, right?
Yes.
Said a minute ago when we were talking about describing that number line, start here, stop there, right? If I know that the way I read the thing is left to right, that's all I really need. Start here, stop there, right? So that's what this says. Start at -1, start shading, start including stuff at -1, and then go until you get to 3. So this is, again, everything between -1 and 3, because you start at 1, you stop at, or start at -1, stop at 3. And then the only other thing we need to write down or capture or express is that difference in the 2 endpoints, right? The one's included and one's not. The one's or equal to and the other's strictly, less than. So the way that we do that is with these things. Square bracket means closed or included. Parentheses mean open or excluded. Right, so one of these is less than or equal to or greater than or equal to, the other is strictly less than or strictly greater than. So there's a couple things there. One is that you're reading it left to right. So smaller thing to bigger thing, right? So you would never write something like 3 comma -1, because that's not the way that we order things, right? We order things the other way around. So there's that part of it. The brackets versus parentheses thing, that's just it's the way we decided to do it. You just got to get used to it kind of thing, right? There's not like a good intrinsic reason for that. It's just, the symbol that we use. So that part, I would say this week's homework and stuff, as you're working through stuff, if you do something and get it wrong, that might be the very first thing you look at. Like, did I do the bracket parentheses thing right? Because that's going to be, a thing that would be a fairly common mistake to make. Okay, so that's that then. For something like what we did here on this third example then, where we said, okay, it was all the real numbers, it's everything, right? Well, how can I write that down using this new idea of interval notation? If it's start shading and stop shading, was there anywhere I should start? Or anywhere I should stop? Not really, it's kind of just always do it, right? Okay, well, how do we express then in math terms the idea of always, or forever, or just keep going? Infinity, yeah, perfect. Those little sideways 8 things, right? So I'd want to go from negative infinity to infinity. That means on your number line, just keep going to the left as far as you want, right? All day. Can't go far enough. And same idea to the right. How should I close that interval up? Parentheses or brackets? Why? It's infinity. You can't actually get there, right? It doesn't end. You don't get to infinity and stop. So because of that, we use parentheses, because brackets would seem to imply okay, we just go to the number infinity and then you're done, right? But you can't do that. Again, that's another one of those things that if you goof that part up for right now, don't sweat it too much. Just, oh good, that happened again. Okay, well, I work on that.
I guess let the screen go blue.
Yeah, I'll work on that. You guys take a look at the last example there at the bottom, example number 4. The QR code on the front will pull up that graph. So you can turn that on so you can see the graph we're talking about. And then what I want you to do is, again, rearrange desks and stuff so you can talk to each other, groups of four-ish. See what you come up with for the domain and the range and all of those other things based on that graph. That's all you need. Everything's right there on the graph. You don't need anything else. Just look at that graph, see what you come up with.
Oh, I see it here.
So yeah, if you pulled it up in Desmos, just click on the little open circle thing next to where it says example 4. So
Yeah, that's Oh, yeah.
Oh.
Oh, no, I'm saying,
I was just saying.
Yeah. Okay, so when we set up the coordinate system, right, we set up the plane. We take one number line called the x-axis this way, horizontally. We take another number line we call the y-axis vertically, we cross them, that's where the plane comes from, right? So x values are always that way horizontally, y values are always vertical. So when we talk about the domain for a function, we mean all of the x values that it sort of covers or includes or like can accept, right? So what is that here, and more importantly, why?
Negative 1, 2, on the left side, we have parentheses, the right side, we have bracket.
Okay, why?
Because the negative 1 is open.
Okay.
So it includes 1, and then the 2 is closed, so, oh, actually, wait, it would be the other way around, right?
You did this part right.
I just
Yeah,
explained it
yeah.
wrong.
Yeah, you mean doesn't include -1, but does include 2, yeah. Yeah, so doesn't include -1, so we get as close to it as you want, but not actually -1. Does include 2. Does everybody see why that's the domain though? Why it's everything from -1 to 2? Or why like this isn't in the domain?
Because it's only in the x-axis, it's how far out.
It's what it covers on the x-axis. So a couple of ways you can think about that would be like, if I'm walking along the x-axis holding a like big tall pole, right? If I stand somewhere, would that hit the ground, right? Well, here the answer is yes, right? Because there it is, it hit the ground. That means that that spot you're standing on, you know, -1/2 or whatever that is, that should be in the domain. So stuff out here should not be in the domain, right? Because my big long dotted line doesn't hit the graph anywhere, but it does starting here and then everywhere to 2, and then that's the last place you see it, right? Another way you can think about it, if you like this sort of analogy or image better, is that if you took this graph on like a piece of silly putty or something, if you smashed it all down, straight down onto the x-axis, right? Then where would the like shadow of the graph fall, right? So if I squish it all down into the x-axis, what happens? Well, everything kind of ends up right there, right? The whole graph, if I crush it down to the x-axis, ends up covering up this part of the axis. Well, that's -1 to 2, right? That's that interval. Okay. How do we do the range then? It's the y values. So you do it exactly the same way, but when you look at the graph, you turn your head to the side. So everybody look at the graph and, you know, put your left ear as close to your left shoulder as you can. Do it. I get to assign you grades later. And then do the exact same thing. What's the lowest it ever gets?
-4.
It's actually a -1. I know it's covered up
Oh.
on the thing. Yeah. No, I know it's, yeah, but don't worry about that part right here, right? That's the lowest it gets, is that place right there. And then the highest it ever gets, 3. Or again, if you like the smashing it all down onto the y-axis thing, it'd be everything from there to there. So how do we write that down? -1 to 3. Okay, then we got to decide about parentheses and brackets, right? Okay, 3 bracket for sure. Everybody cool with that? Because there's actually a point there saying like, you know, -1. Do we have any reason from the graph to think that that's not included? Namely, what I mean is there a big open circle there saying like, don't include this point? Okay. For right now, we'll adjust this later on, but for right now, if it looks like it's included, then it is. If it's not, then it's gonna look like it's not. Okay, yeah.
When did you get -1?
That's this point. This is -1.
Oh, that's -1?
Yeah,
Okay,
I-
so I was counting wrong. I was counting.
yeah. It's easier to see if you look at, like, actually pull the thing up in Desmos because you can move it around,
It won't,
but it's like covered up by the thing. Yeah, so that's -1. And then 3 is the highest point. Everybody feel, medium okay with that? Okay, that's good for now. And then you'll, of course, get plenty of practice with it. Okay, let's see if we can answer some of these other things then. So finding the domain and range, that's all about figuring out the X and Y values that are sort of there, right, that are covered. The rest of these questions, what is f of 1? When does f of x equal 3? What are the x-intercepts? What are the y-intercepts? What are we asking about here? What are we trying to find? Specific points. Yeah, we're just trying to find specific points on the graph. So when something asks us to find f of 1, what do we do? Yeah, that's plugging in x equals 1, right? We're just doing it from a graph. The way you do it from a graph is you go find 1 on the x-axis and you see where the function is, right? You see where the graph is. So what's that point that goes with the x value 1? 1, 0 would be the coordinates, right? X is 1, y is 0. So f of 1 is 0, right? It's just the y value that goes with the x value 1.
You want us to put like the actual point it is or just 0?
Yeah, so yeah, there's a little bit of like nuance to that too. Yeah. The question was, what is f of 1? F of 1 is 0.
Oh, okay.
Yeah. No, you're good. So yeah, the point is 1, 0. The answer to the question would be 0. Yeah. How about when does f of x equal 3?
Point.
Is that the same thing? Is that different?
It should be the same because f of x is that's the another way of pointing out the function itself.
Okay. So same thing, except instead of giving you an x value and I want the y, I'm giving you the y and I want the x. Okay, so find y equals 3. There it is. And then figure out where the graph is. 2, 3. So when is f of x equal to 3? When x is 2. So again, it's just, and I think like, by the time we get a little further into things, you'll be shocked by how much of what we do is really just, here's an x, tell me the y, or here's a y, tell me the x, right? Of course, as we go along, like we'll have to work out some details and stuff, but a lot of it does come back to this really. Okay, so what about these last two, the intercepts? What do we mean when we talk about intercepts? Where it crosses that axis, right? So when we say x-intercepts, what we really mean is when you hit the x-axis, or in other words, when is y 0, right? So when does that happen here? Well, right there, we already found one of them, right? Is that the only one?
Yeah.
Got some yeses and some nos.
It's not, it doesn't include that.
This is almost one, right? It's so close, but that open point means you don't actually get there, right?
So only one extra.
You can get as close to it as you want, but the open point means you don't actually reach that value. So it doesn't count as an intercept because we don't actually touch the axis there, right? Think about it as, if I zoomed in far enough, I could see a tiny little gap. Like you can't really, but that's the idea. Okay, so the only x-intercept is that point at 1, 0. What about the y-intercept? because where we cross the y-axis is right there at 0, -1. Good. So again, we're really still just looking at ordered pairs, right? Points, coordinates on the graph. It's just that they get special names because they, matter for some stuff when we're talking about intercepts. Stuff that we'll, worry more about later. Okay, does everybody feel okay about that, or at least, okay-ish? Okay. Okay enough that you can go try to do homework stuff. Yeah, okay, cool. We can work for that for now. All right, great. So what we're gonna be looking at for the next couple of days is some more the detailed stuff with graphing. Kind of, on one hand, like reinforce this idea. I'm just gonna hand out big piles of things and assume that things will work themselves out towards the back of the room. Okay, so we're going to be looking at functions and their graphs and talking about, in particular, a special property called symmetry that we'll work on defining. But again, QR code here tied to a couple of graphs, or you can just graph it yourself. But we've got about 15 minutes left. So what we're going to try to focus on is getting through this first example. So we're looking at a specific example of a function. It's the function f of x equals x squared. Right, so it's the function that takes a thing, takes a number, and squares it. What does it mean to square a thing? Take two copies of them, multiply them together. Right, so that's what this function does. You give it a value, it multiplies it by itself. Again, its graph is tied to that QR thing, or you can graph it yourself. What I want you to take a few minutes to talk about with your group and come up with are the domain and range of that. So just like we just did, from the graph, come up with the domain and range. I've got some points labeled on the graph. I want you to just kind of look at the coordinates. You can write them down if you want, you don't have to, but just look at the coordinates and look for any kind of pattern or anything interesting, or what on earth is Dr. Thomas trying to tell me with these points that he went to all the trouble to label. So what do you notice about those? And then part D, find f of -x. So substitute that in, actually plug it in, see what happens, and see if you can, again, come up with, with your group mates, some kind of meaning for that.
Only have to take 2 minutes.
All right, somebody talk to me about the domain of this thing. Why?
Because it's going up like that, so it's gonna have all
Okay.
It doesn't have any points that stop, it just keeps going.
Okay, doesn't stop anywhere, just keeps going. Remind me your name. Javon. Did this kind of thing with his hands, like if you were going to draw this thing, you put little arrow heads on the end of that thing, right? The part that we're interested in is not that it's going up, but that it's going out, right? Okay, yeah. So just make sure, because we are taking this two-dimensional thing, and when we talk about the domain and range, we're basically breaking it down to a one-dimensional thing, right? One of them this way, the other one this way. So domain's x values. So, or again, if you like, you can do the, if I smushed it down onto the x-axis thing, what would it look like, right? Well, here it is zoomed way, way out, right? There's a big picture of what this thing looks like. Based on what we see here, if I smush this whole thing down onto the x-axis, does everything get covered up, or does stuff get left out? Everything gets covered up, right? So the domain is the whole real line, all real numbers, or negative infinity to infinity, right? Those are always the same thing. Is everybody okay with that idea?
Okay, what if we did it wrong? Because we talk about -3 and +3.
Okay, so those are some of the points that are marked, right? But it doesn't end there, right? It continues going past that. So that's how this is different than that last example. The last one we looked at, it stopped there, right? It cut off. It was like I took a graph like this and I just chopped the ends off, kind of, right? This one keeps going. Because it continues going, we, sort of go with it, right? All right, so let's write that down. Those are infinities. What about the range? Same idea, but the other way, right? We want the y values. So the lowest point on this thing is 0, and then from there it goes up, right, to infinity.
Is it okay if we write all those numbers or do you want us to write it?
Yeah, no, that would be fine. All real numbers would be fine too. This came up in one of the morning classes too. The one place that it does, quote unquote matter is going to be for doing online homework stuff because it wants you to, answer a particular way. So look out for, it might say like answer using interval notation or something. That means this, right? Negative infinity to infinity. If it's something that you're handwriting that I'm grading, I'm good with either one because I know what you mean, right? What you're saying. Okay, so I marked some points here. Let's see what they are. Negative 3, 9, 3, 9, negative 2, 4, 2, 4, negative 1, 1, 1, 1, and 0, 0. And what I asked you to do is very vague, right? I just said like notice things. What do you see happening there?
Is symmetrical.
In what way, or what do you mean?
Well, so where the point negative 3, 9, there's also negative 3, 9, there's also 3, 9.
Yeah, okay, so all the points I marked have a buddy, right? Yeah, so it is symmetric, and even more than that, I can describe how it's symmetric, right? It's relative to a vertical.
You square like the first number.
Because what the function does is square, right? So what this function does is square. What happens when you square things? You take two copies and multiply them together. So what if the thing was positive? It's a positive. What if it was negative?
Okay.
It becomes positive, right? And if it was 0, then you get 0. Huh, weird. So that's what we see here. Negative 1, 1, 1, 1. Well, that's because negative 1 squared is 1, and 1 squared is 1. So they go together, right? They pair up. The symmetry thing is that, yeah, if I hold the line down the middle, the y-axis, if I hold that still, if I either flip the graph over or maybe think about it on like a sheet of paper and fold it over that line, what do those two sides of the graph do? Yeah, they like mirror each other, right? So if I fold it in half or something, they line up. They're exactly the same. They're mirrored around the line y equals, or around the y-axis. Sorry. So the thing to notice is that symmetry, right? So I'm just going to write y-axis symmetry here. Dang it! Of course it did. All right, we're gonna have to figure some other kind of. We're gonna have to figure some other kind of solution out here. That's not gonna work. Just 3, I think. Okay, so we get this y-axis symmetry. The last part. Man, what an annoying thing. But the good news is that this is the class that I'm recording. So, this will all be there too for future generations. Okay, anyway. So we've seen this symmetry and that these things kind of pair up and like everybody's got a buddy on the other side, right? Again, it's not just the nice, neat coordinates that I marked, but it's all the other stuff in between too, right? This last part, finding f of negative x. Well, think about it just as, an evaluation. So replace x with whatever you're plugging in. Well, what the function does is square things. So this would be something squared. Right? If I plug negative x into this function, what that looks like is take negative x and square it, right? But squaring means take two copies and multiply them together. And what happens when you do that? The negatives go away because you're multiplying a negative by itself, right? So you get x times x, but we usually write that as x squared. All right, now this is a place where you can kind of get, because you go into like doing algebra mode, right? Just doing the symbol pushing and you kind of forget about like what's actually going on. the thing to notice about this is that it is exactly the same as what we had in the original function, right? This and this are the same. What that actually means is that it's not just those couple of points that I marked on the graph. And it's not just the stuff that we see right in the like normal, like default window or whatever on that graph that works for, that they, pair up like that. What this says is that f of x and f of negative x, well, those are points that are on opposite sides of the y-axis from each other, right? That's a point over here and a point over here, the same distance away. And what we just found is that the function value, which is the y value, right, which is like the height of where it ends up, is the same for that and for this. That's this y-axis symmetry. That's like proving that it works for everything, right? That there's not some random place out at, when x is 10 bajillion, where like suddenly things start working differently, right? But that it does it for everything. Functions that do that are called even. And again, a couple different ways we can see that f of x and f of negative x are the same. And they're also y-axis symmetric. Also, a fun fact about this one, it was x squared, right? So the power on it was 2. What kind of number is 2? So your homework's going to be doing example number 2 here for tomorrow. The function we're looking at there is x cubed. What kind of number is 3? So what kind of function do you think x cubed is going to end up being? Odd, yeah, okay. So you get to go home and figure out the details of what that looks like, but work through basically all of the same stuff. Like just like what we just sort of talked through. Pull up the graph, look at it, figure out what its domain and range are, look at some points, look for patterns, look for the same kind of stuff that we've just been talking about, and then try to do this thing, right? Plug in negative x, see what happens. Look for, like what that means. All right, we will pick up there tomorrow. Y'all have a good day, and I will see you then.